Hello, my name is Javier Garcia and I will be presenting on my project, Checkpoint-Based Control of Underwater Autonomous Vehicles. Autonomous underwater vehicles, or AUVs, have seen increasing use in places where humans would find it difficult to reach or be able to operate, such as maintenance, inspection, and exploration in subsea environments. However, disturbances in these environments, such as ocean currents, present a challenge from a control perspective. Furthermore, data for this current modeling might not be available to help update the models used to control the robots. To make things worse, there's a lack of GPS or other similar positioning systems underwater. Acoustics that are usually used for longer range communication suffer from path interference, and optics can be easily obstructed by obstacles, preventing camera vision from being used. There have been several complex approaches that have been explored in order to solve this problem. In some papers, dynamic slide mode control has been used to keep the AUV on a desired path. Waypoints can help with the positioning problem. On the right, you can see an AUV that is moving towards a waypoint, but some components of its motion are moving it away from the path. Another approach is using modal predictive control, where the goal is to keep a reference quantity like velocity or acceleration close to a reference. Other techniques, such as fuzzy controllers or neural networks, have been used for nonlinear and more complex tuning of PID controllers. These techniques have shown a lot of promise. However, for the purpose of this project, a simpler AUV model based on some of the literature is implemented so that some of the techniques covered in class can be implemented and tested. Based on the literature, the most common objectives identified are to estimate the current to update the AUV model and also to eliminate the lateral deviation from the desired path. The problem setup is as follows. We assume that the AUV can measure its acceleration using something like an IMU. We have no access to positioning information such as GPS, so the AUV will use dead reckoning most of the time. The AUV can detect checkpoints when they are a certain distance from them, similar to a beacon. Once in range, they can calculate the relative position with good accuracy. This allows the AUV to reposition itself and be able to start the next motion from a known position. Locations of the checkpoints are fixed and known, and the ocean currents are assumed constant while the AUV is traveling between two checkpoints. This current can, however, change when the AUV is repositioning to move to another checkpoint. You can see on the bottom picture 2 examples of beacons that could be used in the form of magnetic induction antennas that we use in some of our other projects. Furthermore, the AUV is considered holonomic, meaning that we can control its lateral motion without the need for rotation. A lot of AUVs these days have these capabilities, so this is a very reasonable assumption to make. The heading of the AUV is determined using known locations of the checkpoints and things like compasses and magnetometers. In the undisturbed case, the robot should be able to reach the goal just by moving forward. However, due to currents, the robot will experience some sideways motion. Similar to prior works, the focus is to reduce this lateral motion so that we can keep the robot on the desired path, otherwise known as station keeping. A picture on the right shows the components of undesired forces moving the robot away from the t-vector, which is the desired motion. If we can eliminate these forces, then the robot should stay on the desired path. 3 techniques are studied, implemented, and tested in this project. These are incremental estimation, recursive least squares, and model reference adaptive control. First things first, we want to develop an AUV dynamic model so that we can implement these controllers on our simulator. The AUV is simplified to a point mass. Its acceleration is dependent only on thrust, current, and drag. This is actually a simplified version of the equation 1 in one of our references. The Coriolis forces, rotations, and buoyant forces are not considered. You can see in the equation below, the force on the robot is simply equal to the thrust plus the current plus the drag term, which is a nonlinear term. The direction of the current is transformed to the local frame of the AUV so that we can apply our station keeping concept. You can see the frame of the robot is moved by theta on the z-axis, and so we transform the x and y components of the current to the F and L components, which stand for forward and lateral. There are actually 2 models that are implemented in the simulation environment. We have the reference model and the true model. The reference model is disturbed by the estimate of the current, while the true model is disturbed by the true value of the current. Because the drag term is a nonlinear term, we linearize the system to make it easier to compute the velocity and the position of the robot at a certain time step. This is done by assuming that the acceleration is constant during a time step and calculating the velocity and the positioning at the next time step using linear acceleration formulas. If the time step is small, this approximation becomes more accurate. A PID controller is applied to the theoretical position of the reference model so that we can get the reference thrust. Limits on the reference thrust and the actual thrust are placed to account for physical constraints, which helps us prevent large changes and instability, and it's also more representative of the true behavior of a robot. The current G true is constant while the AUV travels to a checkpoint but can change between trajectories. Here you can see an example of the simulator where the true AUV, which is the blue box, moves, and it's actually moved to the side because of the current, which is shown as the black arrows. The reference AUV, which is the semi-transparent red box, does not see this current because its reference current is 0 in this case, so it moves forward without any issues. The solid and semi-transparent green spheres represent the checkpoints and the detection range of these checkpoints. Once the AUV reaches the semi-transparent sphere, it can determine its actual position from the checkpoint and correct so that it can start the next movement from a known state. Now we can begin discussing the actual approaches we are applying to try to solve our control problem. The first approach is incremental estimation, or IE. When the true AUV is outside of the detection range of the checkpoints, its thrust is set to that of the reference model, which is calculated by simply using the theoretical position of the model. When the true AUV, however, reaches the detection range, the positioning error is used to update the current estimation for the current. In this case, delta S, which is equal to the true position of the AUV minus the reference position. Once that delta S is computed, we use it in a constant linear acceleration formula to try to obtain the error between the current and the estimated current. Now, of course, this is not completely accurate because we are ignoring the drag term here, but this is counteracted by the step size parameter alpha that we can tune so that we can have our estimation be better. This is similar to action value estimates, where the new estimate is computed by adding the error between the target and a null estimate to the old estimate. The reference model uses these new estimates for the new trajectories, and every time the new estimate is computed, the reference model becomes closer and closer to the true model. You can see here an example of this approach working. As the true AUV reaches the detection ranges, the current estimate evolves, as you can see on the top right, and eventually it becomes really close to the actual current, which results in the true model and the reference model following pretty much the same path. The second approach is recursive least squares, or RLS. The main disadvantage of IE is that if the true AUV never reaches the detection range of a checkpoint, then the algorithm fails and the AUV risks getting lost. Instead, we can use accelerometer data from the IMU to estimate or to update the estimate of the current every time step. Here we see the equations from before modified slightly so that we have a parameter theta as a function of the measured acceleration, the reference acceleration, and the current estimate. We can use recursive least squares on this estimate theta so that we can get a new current estimate every time step. We can see the RLS equations, and then finally we have the new estimate for theta equal to the previous estimate plus the recursive least squares term. Here we see an example of the second approach working. You can see that the current estimate changes as the robots move, as opposed to waiting for the robots to reach the detection range. Overall, the true AUV stays closer to the path, closer to the reference model, which greatly diminishes the risk of the AUV not reaching the detection range of the checkpoint. Last but not least, we have Model Reference Adaptive Control, or MRAC. Instead of directly estimating the current to update our AUV model, we can modify the command signal to counteract the impact of the current. In this case, the reference model is assumed to have no disturbances, and the MRAC attempts to mimic its response. You can see in the equations that the reference model does not have a current term anymore, and that for the actual AUV, we have the current is incorporated into the input. Since we have unmodeled dynamics and we want to guarantee stability, we choose the Lyapunov approach, and so we compute the error and the derivative of the error between our true and our reference models, and we use a Lyapunov function so that we can find the update rule, which you can see on the left. On the right, we have the corresponding block diagram used to implement this particular MREC to our system. Here you can see the MREC working. You can notice on the top right that there's no actual current estimation, which is different from the IE and RLS approaches shown before. But that being said, the true AUV follows the reference AUV very well. And that's because, once again, the MREC is attempting to mimic the response of the reference model without any current disturbances by modifying the input that goes to the true AUV. In order to determine which of the approaches works best, we test them in different conditions to determine which one has the least error or which one is the most robust. We use the path that is shown for the following tests. We have 4 checkpoints, and the AUV moves in 6 different trajectories between them. In the first set of tests, we vary a current variance term. The mean value of the current is equal to 0.15 and 0.1, and then that is we add the current variance to that. The current changes every trajectory, as has been mentioned before, and we study different values for the variance of the current. Every value is tested 100 times for each approach, and then we have the average error between the reference and true AUVs at the different ranges, and this is only for the runs that have been successful, because we also have the success rate of the approaches, which is an equally important metric. So once again, we have on the x-axis, you can see on the right, we have runs, and this basically means what the error was when the AUV completed that particular run, right? So you can see that when there is no current variance, so the value of the current is exactly the mean value, RLS and MREC perform well, and IE does not perform as well, but it does perform, and we have 100% success rate, and this is our control results. And then we start increasing that variance for the current. So we see with 0.05 variance term, IE starts failing. Not a lot, but it does fail sometimes. MREC and RLS still perform just as well. And then when we keep increasing that error, IE starts failing more often. When we have the larger terms, 0.25 and 0.5, we can see that RLS begins failing as well. So we suddenly drop from 100 to 75, and then for the larger value, we actually have a dramatic drop to 13%, and IE also in the single digits at that point. MREC, however, manages to have 100% success rate and keeps the average error very low still. To further test the performance and robustness of RLS and MREC, we introduce a measurement variance term, since they do depend on the measurement values to function. So we test the performance for different values for this variance term, and most everything else is the same as in the previous tests. We have 100 tests for every case, for every approach, and the mean value of the current is set to 0.15 and 0.1, and its variance is kept at 0.1. We can see on the right our control with a 0 measurement variance, so the measurements are exactly what the state of the robot is at that time. We can see that both of the approaches have a 100% completion rate. MREC still outperforms RLS in terms of error, but as we start increasing that measurement variance, we see that the RLS starts failing. With just a little bit of a measurement variance, we already see some failures, and as we keep increasing that, the success rate of RLS drops very fast. And finally, we get the very large values with only 4% of the tests out of 100 completing 4.05, and then for 0.1 the RLS is not able to complete a single run. Meanwhile, MREC is capable of having a 100% completion rate, and it still has pretty similar error values all throughout. From the previous results, we can see that as the current variance increases, the simpler IE approach fails very often, which is not a surprise because once again, IE only updates the current estimate when the true AUV reaches a detection range, so it is very susceptible to not reaching the range when there is large disturbances or where the trajectories are very long. Since RLS continuously updates the model of the system, it performs better than IE, it's more robust, and when variances are large, it has very, very good error results. That being said, MREC is the most robust by far, not failing once even with the larger current and measurement variances. RLS is also very susceptible to measurement variance, even more so than current variance. Once the values started going up, the success rate of RLS dropped dramatically. Tuning its forgetting factor gamma could help in some of the more extreme cases, but one of the points of this project is that there is no previously known information about the currents, so that would be a little difficult to do in advance. That being said, the impact of the values for the different parameters for the approaches could be studied more extensively, and that is something that could be done in the future. For all of the tests done, the same parameters were used for all the tests for the different approaches, and these values were all obtained empirically through trial and error in the simulator. Once again, only 2D control was explored in this project due to time constraints, and once again, AUVs can quite accurately determine their depth using pressure sensors, so controlling the Z direction was not a big concern, at least not in this project. So what about iterative learning control, or ILC? Originally, I had planned on using the ILC algorithm to counteract the effect of the current by modifying the input sequence similar to MREC. Although the AUV trajectories are not the same, the current disturbance is pretty similar on the global axis, on the global frame, if the variance is low. And so the idea was to get the corrected input sequence after a trajectory and then transform that sequence back to the global frame and then to the local frame of the next trajectory. And the hope was that we would be able to use that corrected input sequence. Also, the input sequence had to be stretched or squeezed because sometimes the trajectories, or a lot of the trajectories, are different lengths. However, you could see that the results are not great. After a couple of runs, a couple of trajectories, there is a control effort that is applied to the AUV, and it does help it go back to the path, but soon after it fails. And so there's two very potential reasons for this. The first is that the filters that I applied were just the filters that we saw in some of the class examples, which might not be applicable to the system. And the second is that the way that the input sequence is transformed might not be ideal. There is some promise to this approach. However, MREC already performs very well, so that would be the approach that I would recommend overall after all the work in this project. Here are the references, or at least most of them, that were used on this while I was working on this. Thank you so much for listening to this presentation. I hope that you have a fantastic rest of your day.